Hey everybody, it's Mr. N here, and we are going to do this lesson on translations. And basically, let's go through a little bit of review here and vocabulary. A translation, right here, is a transformation that glides all points in a plane the same distance and the same direction. So we're going to take everything and we're going to slide it the same distance in the same direction. So if you have a triangle, such as this, let's draw one up here, you would just slide the whole thing, say that direction and that distance. Now, direction and distance, we've got this quantity called a vector. Okay, a vector has both magnitude and direction. Wait, didn't the guy in the Minions say that? That was his name, Vector, and he said he's got both magnitude and direction. Okay, so he's got size and direction. I would show you that little clip, but there would be copyright issues, so I can't. But you can look it up. Anyway, a vector is usually expressed by drawing an arrow or 2 points. To 2 points, sorry. So this would be vector from A to B, and we'd say vector AB, like that. Okay? And now vector AB, right here, would be the vector 8, 6. So we write it as the change in x and the change in y. So vector AB would be 8, 6. Notice the notation. We use these types of brackets. So over here, on the next example, let's take a look at this. In this diagram, over here, we've got P to Q. And let's do it in green, since it is green. And we've got vector PQ, like this. And this vector would be 5, 3. Because we go 5 to the right, that's our change in x, and 3 up, that would be our change in y. Magnitude, that's another word. So a vector has both magnitude and direction. What does magnitude mean? Magnitude is pretty much how far it goes. So we denote it with this thing. These are not absolute values, but they look like it. It just means magnitude. So this means the magnitude right here. Magnitude of vector AB is what I'm saying there. Now for magnitude, we express it like we do the distance formula. The magnitude would be, now if I had my original vector AB, which was 8, 6, right? The magnitude would be the change in x, the change in y, that's 8, 6. So this is our magnitude, which is that distance. So it's all a bunch of like fancy words for us right now. So how do I get that distance? Well, that's the square root of 8 squared plus 6 squared. Right there. Work it out, you get 10. So the magnitude of vector AB, that's what that means, is 10. Now, a scalar is a number that I can multiply a vector by. For example, I could say 5 times vector AB. Okay? So now I'm saying it's going to be like having 5 of these ABs lined up, 5 times it. Now, 2 vectors are equal if they have the same magnitude and the same direction. And what do I mean by direction? We're not going to focus on direction a whole lot, but direction would be this angle that's formed. Okay, but for right now, we're not going to focus too much on that one. Now, how do you add 2 vectors? Okay, so that would be a vector sum. So let me give you an example of how I would add 2 vectors. If I had this vector right here, we'll call this vector x, y, and I had another vector right here from y to z, well, the addition of these two would be this new vector that's created. Now look at this. If you break this up, it's gone this distance in the x right here, plus this extra distance in the x. let me do that with another color. So it's gone this total distance in the x. In the y, it's gone this total distance. So this brand new vector sum, what you're going to do is you're going to add the x's and add the y's together to get that. So up here, if you have vector AB and BD, you would, to add these two vectors, okay, you would take the corresponding parts, A and C, these are the x's, add the x's together. These are the y's, add the y's together. And that would be the resultant vector from A to D. So let me draw this out for you. So if you had vector AB and vector BD, this would be the resultant vector AD, and you just add the x components and the y parts. Okay? So now, we usually follow the vertices along a vector, so you can, if you have this vector like this, it's telling you move everything, all of these points to there. You could do that. Now a translation is a transformation along a vector such that each segment joining a point and its image have the same length of the vector and is parallel to the vector. So remember we said it has to be the same length and the same direction and all that? Well, that's how we can make a translation. We will move it along the similar vector. So typically we denote the initial point with just the letter, and the new point we will put this little symbol on it right here, which is called a prime, and that's usually the new point. Okay, so we go from the original to the new along a vector. So we're basically just moving the point. So I could take point A and I can move it, say I have a vector right here. I'll make the vector go down this time, and suppose I want to move point A, I can slide point A down along this, and I will get my new point right here, which will be A prime. And now if there's any other points attached to A, they all move like that. So if I had a square, for example, they would all move that same distance to create the new shape, just like I did up there. So now let's suppose we're going to do some transformations. For a translation, something that I'm going to slide along a vector, I use the letter T. That stands for translation. So if I have points A, B, and C, and we move these each left 3 and up 1, I can write this as a translation such that xy goes to x plus a, y plus b. Okay, let me write the words out for you here. This T means translation. This means such that, okay, x comma y maps to x plus a, y plus b. That's the terminology there. So let's shift this up and you can see. So recall that a vector in a coordinate plane can be written as AB, where A is a horizontal change and B is a vertical change from the initial point to the terminal point. So where we start the vector, it's called the initial point. Where we end the vector, it's called the terminal point. So here is a translation, and they didn't quite write it here in these examples the way I want you to. This is a translation such that x comma y maps to x plus a comma y. So notice I only went from point P to P prime. I only moved a distance of a. I did not move any y distance. This one, a translation such that x comma y maps to x comma y plus b. I only moved from point P here vertically upwards. Now this one moves horizontal. Let's do it in another color again. This one moves horizontal and vertical. So point P starts off here and ends up P prime right there. So that is a translation such that your x comma y maps to, it moved x plus a, and then it moved up y plus b. So that is the translation there. Well, we know a translation is an isometry. Okay, well, what the heck is an isometry? Isometry is a pretty fancy word. It's a fancy word for congruent. It just means congruent. It means you're not going to change the size, you're not going to change the shape. But typically we use this word isometry when we're talking about some sort of transformation. So that is associated with a transformation when I say it's an isometry, rather than just congruence. Congruence pretty much means the same thing, but isometry, we're going to say, oh, okay, he's talking about a translation. And so all these right here, let's highlight it. I'm kind of talking a little slow today because there's a lot of vocabulary. I want to make sure you understand it. Reflection, translation, rotations, those are all things we're going to learn. All of these are isometries. And isometries is also called a congruence transformation because it's congruent. And we can also call it a rigid transformation. So there's three things: isometry, which means congruent, and a rigid transformation. They all mean the same. All right, so let's continue on to the next page here. We've got some things here to talk about. A rigid motion, which is what I just discussed, is a transformation that preserves length and angle measure. So a rigid motion would be an isometry. Right here, rigid motion is an isometry. So we're just moving something and it doesn't change the size or shape of it. That's what a rigid motion is. A translation is a rigid motion, and the composition of two rigid motions is a rigid motion. What do I mean by that? Well, that means I'm going to move it here, and then I'm going to move it here. So that's a composition of two separate things. So it's two motions, and it's not going to change the size or shape of it. You can have more than two. I can move it here, I can move it up, I can move it over, so you can have two or more. Okay, two or more, and we'll discuss more of these later, but let's talk about this first kind, a glide reflection. This is like making two transformations, and so the two transformations are a translation where we're going to slide it, we call it a glide, and then a reflection where we're going to flip it. Okay, so we glide so that each point A maps to A prime, B to B prime, etc. Then we're going to reflect. So now look, I'm going to take these new points, A prime and B prime, and they're going to end up going to double prime. So that's the second transformation. Notice I put two primes because that's the second one. Two primes, that's the second one. And when I do some of these examples, it'll start sinking in. The hardest part of this is understanding the terminology. Once you get the terminology down, it's pretty simple. So let's take a look over here, and we're going to do these additional examples together. And on the first one, it says if translation t such that 1, 3 maps to 5, 1, then t such that 2, 8 maps to what? What are these two answers? Right here, maps. What maps to 2, 8? Well, remember, a translation, I move in the x, I move in the y. I moved from 1 to 5. So the translation was 4. That was my vector along the x. And I went from 2 to negative 3. That was negative 2 along the y, right? So I went backwards 2. So 2, 8, the translation such that 2, 8 would map to, this would be 2 plus 4, comma, 8 minus 2, so this would map to 6, comma 6. So now, to do the next question, let's do it in a different color right here. What map to 2, comma 8? Well, remember, I added 4, so now I'm going backwards. I'm going from 2 back to where I was, so I'm going to subtract 4. So this would be negative 2, comma, and then I subtracted 2 in this direction, so if I went backwards, I would have to add 2, so this would be 10. So negative 210 mapped to 2, 8. Because if you do it like we did over here, this was our original that we were given. I added 4 here, and I subtracted 2 there. For the next one, let's take a look at what we got. If the translation negative 3, such that the negative 3, negative 4 maps to negative 6, 1, then what translation maps to 4, comma 8? Now look, from negative 3 to negative 6, I subtracted 3 in that direction. So if I go backwards, I'm going to add 3, so this would be 7, comma. Over here, in the forward direction, I went from negative 4 to 1. So that means I added 5, right? That's how I get from negative 4 to 1. So if I go backwards, I'm going to subtract 5. So 8 minus 5 would be 3. That would be this new, or the translation that mapped to 4, comma 8. Okay. The translation R maps P to P prime, and S maps P prime to P double prime. So now we have two things going on. Find T, the translation that maps P directly to P double prime. So R is from P to P prime, and then S goes to P double prime, right? So together, to map the whole thing, I'm going to add the X corresponding values, add the Y corresponding values. So P mapping directly to P prime would be the translation such that XY maps to, now we're going to add the X components. This would be X minus 3 and X plus 1. I subtracted 3 from the X. Don't add the X's. Just add what you're doing. I subtracted 3 from the X, and then I added 1 to the X for a total of X minus 2. Now over here, I added 2 to the Y, then I added 7 to the Y for a total of Y plus 9. So that's why we keep the X's and Y's like that. So it's mapping X. The two things that it does together ends up being minus 2. Y, the two things that it does together, it goes plus 2, then plus 7. We're going a total of Y plus 9. That is this translation. For the next one, let's take a look at it. Over here, X plus 1, and then X minus 4. So this new translation, XY, would map to, I'm adding 1, subtracting 4, so it would be X minus 3. Over here, subtracting 3, subtracting another 3, Y minus 6. And I'm going to go ahead and stop here. I'm not going to do this last one with the glide reflection because I'm going to talk more about the glide reflections in the next couple sections, and we'll do those in more detail. So we'll stop at those with those examples. We will do the student journal ones in class, and we will go from there. So thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.